Well, we are back, so it is my great pleasure to introduce Brian Searle to you. So Brian completed his PhD in the McCost lab recently, relatively speaking, right?
Yeah, actually, about a year ago.
Well, here you go. And Brian, of course, is extremely experienced in all things mass spectrometry and proteomics, and his recent interests are specifically in DIA. He is now working at the Institute for Systems Biology in Seattle. He has his independent position, and we're really happy that you're here with us. Thank you very much for coming.
Thank you. Thank you, Olga. Perfect. Yeah, so I actually did my dissertation backwards, or my career backwards, and started at Proteome and then went back for a PhD very late in life, realistically. Okay, so before we started, I want to ask a couple questions, because this is the first kind of like real training session so far. First, how many of you have collected DDA before? Most of you. Awesome. How many have you collected PRMs before? You guys are pretty sophisticated. Cool. Okay. Anyone collected DIA yet? A couple? Not bad. All right. Better than, actually, this is probably the most experienced crowd that I've seen. So for tomorrow's tutorial, we're actually going to do a walkthrough in Skyline with a top data set and an Orbitrap data set. This will be the first time I've done it live, so we'll see what happens. But there are a couple options. So I'm curious, how many of you use TOPS and how many of you use QTOPS? So TOPS, and then QE style instruments are fusion style instruments? Okay, so it's a nice mix. Okay, cool. So let's get started. So if you wanted to go to the library and check out one of my favorite books in the Harry Potter series, you might be interested in trying to read this, go to the library. The way you definitely wouldn't go about trying to find Harry Potter in the library would be to yank a bunch of books off the shelf, maybe the largest physical books that you could pull off, and grab them in a cart, and then go through them one by one and say, okay, there's Moby Dick, there's Pride and Prejudice, there's War and Peace, there's Lord of the Rings, there's no Harry Potter in my set of books that I pulled off the shelf. So obviously Harry Potter isn't here, right? I mean, that's ridiculous. You would just go look it up based off of the author's last name, some statistic that you knew about the book ahead of time, and say, okay, it's written by J.K. Rowling, let's go look in the R section of the library, and then try to pull it off the shelf. Okay. So obviously this is hyperbole, but I think this is a really important point ultimately, which is that failing to detect a peptide in a DDA style experiment, or in general, is not necessarily a proxy for its abundance or whether it's actually even in your sample at all. And we've done a lot so far here on SRM and PRM approaches to try to get a true zero. But true zero is a hard thing for us to achieve, to be perfectly honest. It's good to know, when we can't see below that level. So let's sort of talk about the different data acquisition schemes just to begin with. Here is a plane of peptides analyzed with DDA. We've got retention time here on one axis and the precursor MZ on another axis. This is just sort of basically the plots that Rudy was showing earlier, just sort of flipped on its side so we can see some three-dimensionality to it. And that each one of these would be kind of like an MS1 scan. We end up connecting the dots between these guys to say that this is a peak or this is a peptide. But the instrument doesn't really know about peptides or anything like that. What it knows about are these individual scans and individual peaks. And so in an individual scan, at this particular time point, it will say, okay, I found enough signal here to fragment a peptide, and I'll collect an MS2 about that peptide. And it'll do that for the next, and then the next, and the next, and then the next, as it's going through the list, right? And this is a great way to kind of catalog all of the peptides in the sample. But what you end up here with is each of these fragment scans is not necessarily a quantitative scan. All it does is tell you the identity of the peptide. It says this is a reasonable facsimile of what the sequence is. And then you really have to go back to the precursor level data to be able to integrate that to measure how much of that peptide is there. So again, you guys have seen this, so let's go through it quickly. But with PRM, there's sort of a different strategy. You end up picking particular peptides and then figuring out what their masses are and then going and looking for them one at a time. So you'll scan through that list and generate a profile for those fragment ions. All of the fragment ions are associated with them. They're the same fragment ions typically that you see up here, but you stand the ability to be able to measure something where you don't need something to trigger on. So for example, this blue peptide here never got high enough in signal for us to trigger an MS2 scan for DDA. But if we just sit and park the instrument on that precursor mass, we will eventually see some signal. And then the question is that signal actually indicative of a peptide or not? So there you need to see, does this fragmentation match to what I would expect it to match? You guys kind of get this? This is hopefully a review from previous in this course. Okay, cool. So this is really important, and I want to stress why it's important. So for example, this is just one precursor scan from 400 to 1,000 in the middle of my gradient, just on a normal HeLa experiment. And if I were to try to analyze this with the top 12 method on my QE, I might scratch my head because there's a lot of stuff down here, right, that's not in the top 12. And so just to give you a feeling for what that is over time, yeah, we have this ability to dynamically select peptides on the fly, but here is 30 seconds of peptides. These are all, again, precursor signals that are repeating this 30-second interval where I see peaks rise and fall as they're coming off the instrument. This is basically, if you stare at the instrument long enough, sort of what you see. And there are definitely regions in here where you see signal, like there's definitely signal for peptides here, but you would never ever trigger on something like that with the instrument. There just are too many other things that you would be interested in trying to sequence in this time point. And in 30 seconds, or sorry, 60 seconds, we're talking about maybe getting 600 precursors at maximum if we were doing like a perfect job with dynamic exclusion. So if you think the instrument's running at maybe 10 hertz or something like that, that would be sort of the maximum that we would ever be able to get out of this. We're never going to be able to sample that much. And just sort of to re-emphasize this, this is that same 60 seconds of peptides, but I've just picked out all of the peptides who signal, and this is in a, again, in a QE. So any peptide that has a signal above 1E7, which frankly, usually I set my DDA thresholds to 1E5. So this is like way, way lower than that, right? Or way, way higher than that, I should say. In this set, there are far more than 600 peptides, right? There are something like over 1,000 peptides in just this 1 minute of time frame. There are far more signals here than we could ever collect with a DDA experiment. Does that sort of make sense, you guys? Okay, cool. Just to sort of re-emphasize this point, here's a plot of retention time and then precursor tick, indicating where you see the most amount of signal. So usually I don't see very much signal in the very early part of my gradient because that's basically the early part of solvent. Then I see a bunch of signal representing the bulk of my proteome, and then it drops off in this later stage, and then you get to the wash afterwards, right? So one of the things that's interesting, so this is a data analysis of that using this is a QEHFX, that same sample. And we've got here in purple, that's the number of MSMS acquired. And you can see that we saturate that quite quickly. This is where we're scanning as fast as possible. We're at this level here. And we're just sort of trying to keep up. This is where the instrument's trying to keep up. It's basically just trying to keep up across the entire range, basically, right? This here is the number of detectable PSMs out of that batch. So it's a percentage of the PSMs that we were able to say this belonged to a peptide. And if you look at this a little strange, you notice that in this region here, we actually get a higher number of peptides detected than despite the fact that there are fewer peptide signals, right? What's going on here? What does this mean? Any guesses? Yeah.
I would think there's probably more single peptide spectra, but there's no interference.
There's definitely a lot more interference in these spectra from other peptides at the same time. So they're definitely more complex. A lot of the signal is just at that threshold where you're just going to scan over the surface of it with the DDA method, right, where it's just never going to be able to pick the stuff at the low graphs. Here, it's going to stand a much better chance because there just aren't that many species at that level in the chromatogram. Okay? Cool. Okay, so hopefully I've explained why I think PRMs are great, but they're pretty limited. You can only go after a handful of peptides at a given time. And so the question is, like, what if you wanted to try to do a PRM-style experiment across the entire genome? And is it possible to do that and to target every possible peptide in a proteome? As Rudy was showing earlier, yeah, it is possible to do that with these new DIA methods. But there are a lot of compromises in that. And so I kind of wanted to talk to you in this first session about what is DIA and what are those compromises that we have to make, and then how we can analyze this data and sort of what are the caveats of analyzing this data, and then finally, when is it more useful? I mean, obviously we can say DDA doesn't work very well for certain types of samples, but can we do better in these types of experiments? So that's sort of the stuff that I wanted to cover in this morning session. In the this afternoon session. I'm used to this being like a one-day workshop, and that's it. That's all we get. 3 days is fantastic. So tomorrow, I'd like to talk about some more sort of how the data analysis works to give you a feeling for what search programs are actually doing with the data, to give you an interpretation for when you can know when it's going to go wrong, basically. I kind of get bored standing up here. So if you guys have questions as we're going through, please feel free to ask them, and we'll try to do that as we go. It makes it more fun for me, at least. Okay. So we talked about DDA, we talked about PRM, and DIA sort of fits somewhere in between that, right? So instead of looking at a single precursor, as you would with PRM, you end up sort of scanning through and collecting a larger swath, as it were, of precursors all at the same time, by basically opening up the precursor isolation window to some amount, depending on whatever DDA or DIA-based method you're trying to do. So for example, here I'm just showing there's this red section right here that might be associated with this swath or stripe in the data set. There are 3 peptides in this region, and you would see the blue peptide and then the purple peptide and the pink peptide. And then this blue region here would show these 3 peptides instead. And this data obviously is a lot more complex. The MS2s that you get out of these types of experiments are very difficult to interpret manually. And it's very much up to the software to be able to figure out that these particular signals actually correlate with each other and not with a different peptide. Okay? Okay. So as we were saying, DDA is pretty comprehensive. PRM, basically you can only go after a handful of peptides in an experiment, maybe 100 peptides in an experiment, maybe 200 peptides, but not that many. DIA sort of sits as a compromise where you can go after many more peptides than you would with PRM, but you're much better off using a fairly limited range, not scanning for all peptides between 400 to 1600. You're much better off looking at 400 to 900 or 400 to 1000. For quantitation, with DDA, you can't really use fragment ions to do quant unless you're using reporter ions. But fragment ions are going to be the most specific for that particular peptide. PRM can do this very well. DIA can do it maybe not quite so well, but maybe better, certainly better than DDA would be, where you don't actually collect that information at all. Okay. So what do these compromises look like? Really, they come from a handful of constraints that we have on the instrumentation platform itself. So one of the constraints is you can only scan your instrument so fast without sacrificing any of the quantitative measurements you want to make. So typically on a QE, really like the older generation QEs, we can only scan maybe 10 hertz. On the newer ones like the HFX or the Lumos style instrument, you can scan at maybe 20 hertz-ish. On tops, it's a little bit different. You can scan a bit faster, but the quality of the data itself is worse. And in some ways, you might actually do better if you could scan average across a larger region. So that's one constraint. You can only scan so fast, 10 hertz, 20 hertz maximum, really. The other constraint is if you want to do quant on the fragment level, you need scans pretty frequently. So typically with DDA, we acquire precursors every second or every second and a half. And we get really nice traces across a 25-second or a 30-second peak, because you probably get around 20 or 25 scans across that peak. Here, we're much more constrained by the number of scans we can do, and we really do need at least 6 to 8 measurements to describe a peak to be quantitative. And so we need to scan, although we're limited at scanning so fast, we still need to scan that same region at least 6 to 8 times across that 25-second peak or 30-second peak. Okay, so the compromises that we have to make here, first, are accepting a higher level of interference by widening these precursor isolation windows. So instead of PRMs, which you're typically acquiring a PRM plus or minus 0.6 MZ or maybe plus or minus 0.8 MZ, these precursor windows are typically like 24, 25 MZ wide. So they have lots of peptides at the same time. Typically we're co-fragmenting somewhere between 10 and 20 up to 100 peptides at the same time. We also have a lot less time to park the instrument on a specific mass over charge to acquire a particular peptide. So with PRMs, if you know your peptide is very low abundant, you can say, sit and scan on that and inject ions for 200 milliseconds. With DIA, that time will just kill you in terms of being able to get enough throughput to scan across the entire range. So we will never be as sensitive as you could be with PRM or with SRM because we don't have the opportunity to park the instrument for a long period of time. And the third compromise that we really have to make is to limit the area of measurement interest. So peptides that are above 1200, you typically can't go after. It's really hard to go after small proteins, for example, as well. So, so we end up with data that sort of looks like this. This is just like a random peptide that I pulled out of an experiment that I was doing in Skyline. Here is a peptide signature for, or this is a signature for this particular peptide using PRM. We typically see a really nice trace for this peptide. It's a good signal for all 4 of our, or I guess 4 out of 5 of our quantitative fragment ions that we were after. And we see those same fragment ions here in the DIA. It's just really hard to make the call as to if that's a peptide or not. But one thing that I think is actually kind of interesting is, you know, the amount of signal that you're seeing down here is actually reflective of the amount of signal you're seeing here, right? So this is 10 times 10 to the third, and this is 10 times 10 to the third too, right? So this actually is the same kind of data that we're measuring. It's just maybe slightly lower fidelity, and there's other peptides here at the same time to kind of cause interference in these measurements. Okay, so what types of DIA experiments are used? How many of you guys have used MSE before? 1? Awesome. So MSE was probably the first viable DIA method, but that's actually not even the first DIA method either, right? So the original DIA publication was down here in 2004. John Venable in the Yates lab did this on ion traps. They collected these sort of terrible MS2s doing DIA just mostly as a proof of concept, and then did their workup in sequest, just trying to detect peptides out of these very convoluted spectra. MSE came around in around 2005 or 2006. The first paper was maybe 2006. And then after that, there's been sort of a long period of time of different other algorithms and different approaches that have come across. So Pacific, for example, is another method that had fairly narrow precursor isolation windows. SWATH came around in 2012 on the SciX tops. And there have been a lot of different improvements over the years on this sort of methodology. We have a wealth of history to go back to. So I wanted to actually just sort of talk about some of this to give you a framework for what types of things are under the DIA umbrella, because DIA means a lot of different things, realistically. So as I said earlier, one of these methods is this MSE method, or you could call it high-low or all-ion fragmentation, depending on who's branding your platform. So here you would typically collect a precursor scan in which you would measure like a normal precursor scan from 200 or 400 up to 1600 MC, and you would see, tons and tons of peptides. There might be hundreds of peptides in this precursor scan, as we were showing earlier with other precursor scans. And you would end up taking all of those peptides at the same time and fragmenting them simultaneously and measuring them all at the same time. So you end up with these extremely complicated MS2s that contain, as I said, hundreds of peptides simultaneously fragmenting given fragment ions at a measurable level. And so trying to detect a peptide out of this is a feat unto itself. But one advantage of this approach was that it was really sort of the first approach that gave you fast enough cycle time to be able to collect a fragment scan every other measurement. So we would collect a fragment scan every, say, half a second or every second or so. And that was enough to be able to at least draw the shape of the peak and do quantitation at the fragment level. So this, I think, was a fairly revolutionary approach. It just produced data that was just really hard to interpret. And I think that even the Waters reps would back me on that. One big advantage of this is it's an early method that was able to do quantitation of fragment ions, and that we would frequently get quantitative measurements, as I said, maybe every half a second or so. And it would be able to collect peptides across the entire range. The only issue was trying to interpret the data afterwards. It really relied heavily on a program called PLGS, which was basically a giant black box, and very few of us really understood how it worked to be able to detect peptides. So,
I don't think anybody ever really quantified off those product ions. I think that in sort of the parlance of SRM or fragment ion things, they would use the MS1 as the quantitative ions and the MSMS as qualitative ions, just telling them, oh, we got the right peak.
yeah.
And we've done experiments since that really, if you're just using straight MSE, you should not use fragment ions to quantify.
Mm.
You need the extra isolation to make it an advantageous thing.
Yeah, it really wasn't until HDMSE where that became much more of a viability. Yeah, this is definitely a good point. Another early DIA method is called Pacific. This was developed by the Goodlet Lab. And I think this was a really interesting approach. It used ion traps, the Velis ion trap, back in the day. And what they would end up doing would be to collect a precursor scan, again in this methodology, this was in 2009, they would collect from 400 to 1400, and then a bunch of fragment ions. And then they would collect another precursor scan and then continue to tile those fragment ions across the entire search space that they were interested in. And once they got to about 30 seconds, they would have to repeat and go back to the original. So the VELOS was an instrument that scans slow enough that they actually had to do injections, usually about 50 injections to cover the entire precursor mass range. And that was only to get one fragment ion scan per 30 seconds or so. That would basically give you an MS2 once per peptide, but it wouldn't require that you had a precursor to trigger off of. Does anyone know why that would be a benefit?
Could you repeat your question? Sorry. Could you repeat your question?
Yeah. Why would it be a benefit not to be reliant on having a precursor to trigger off of? Because DDA requires that you see a precursor signal before it says, oh, I'm going to select that for peptide sequencing.
You will lose some of the sensitivity if you don't see the precursor. You will never identify anything.
Yeah. So for example, an orbit trap or in an ion trap, an orbit trap can only hold about 1 million ions in it at one time. And if you've got like a really complex dynamic range, such as like the serum samples that Rudy Ebersol was talking about, where 99% of your protein comes from 8 different proteins, then what you end up doing is the instrument collects most of its signal on just one peptide that's eluting at that same time point. And you might have a handful, 10 ions out of your 1 million ions are actually for any other analyte that are associated with any other possible peptide. And in those situations, you wouldn't necessarily be able to see a precursor. However, if you effectively tell the instrument to trigger on that time point or that mass range, then you can still collect fragment ions for that region because there is enough peptide there. It's just it's being masked by these very high abundant peptides that pollute the sample. So Pacific, as the name might suggest, was actually originally developed for analyzing ocean seawater samples, where they were interested in looking at not just one organism at a time, but 10 organisms at a time or 20 organisms at a time. And because of that, there was a huge pollution of the most abundant of those organisms if you ever wanted to see stuff at the bottom. So this gave them a method to be able to collect MS2s on that stuff down in the grass. Albeit it would require 50, 60 injections to be able to get enough signal to do this. So they would basically publish like one sample as their paper whenever they tried to publish with this method. So quantitation was here because they only got one fragment ion or one fragment scan per range every 30 seconds or so. There wasn't enough signal to be able to do quant on fragments, so they had to do it all on precursors. They used the fragment ions just for detection purposes only, but they were able to basically do DDA without precursors here. And so they had very narrow precursor isolation ranges, and because of that, they were usually isolating one peptide or a handful of peptides only at one point, which is a very different story than if you were looking at the MSE data. So a big advantage of this approach was that they could basically put these data sets into sequest and collect and see all of the peptides that they were detected off of that. So it was a very normal standard pipeline that they could use. But they suffered on the other end, which is having to run a whole bunch of injections. Okay, so these newer DIA-based methods, what we call now modern DIA or SWATH, uses these wide window scans. And this is pioneered by Rudy's group, and so it's great to actually have him here to speak about this. Here, they basically would acquire a precursor scan and then a wide window fragment scan. Usually, in the original paper, it was a 25 MZ wide window. And then they would collect a bunch of those, tile them across the entire precursor scan range, and then collect another precursor scan and then do it again. this data, is sort of a hybrid between those last two approaches. Instead of this MSE style messy data, these spectra are almost interpretable. You couldn't necessarily give them to a search engine, but at least you could sort of figure out that a handful of the fragment ions belong to this peptide and another handful belong to another peptide. So, quantitation you could do with fragment ions. You got frequent enough scans to be able to draw the shape of the peak. So 2 or 3 seconds between each cycle time cycle. And that you would typically have to measure a sort of compromised precursor isolation range. They were looking in the original papers from 400 to 1200. So they had to basically sacrifice any peptides that were above 1200. So this was an advantage in that it was a lot less reliant on software to do deconvolution of peptides, but it was still pretty reliant on software to make it understandable. I think the biggest advantage of this, and I think the insight that Rudy's lab provided, was that instead of trying to treat it like DDA data, you could treat it like kind of really bad PRM data, and that you could analyze it using a tool like Skyline, and that's what they proposed and what they went after, and what we'll show you here today, or this 3 days. Okay, so what does DIA look like in a modern experiment? As I said, people typically now will maybe measure from 400 to 1,000, at least in the McCoss lab and the McCoss lab surrogates. And these fragment ion scans would typically be 25 MZ wide windows or 24 MZ wide windows. And then you would collect them sequentially, one after another. So here I'm just showing you 25, 24 MZ wide windows. If I can collapse those guys down here, so there's about 2.5 seconds in between each of these fragment ion scans. And if I were to collapse these down, you would end up seeing this, and then these would be repeated. So each one of these fragment ion scans would be, as I said, 24 MZ wide. So this would be 784 to 808 MZ. And here, if you looked at one of these scans, if there was a really high abundant peptide, it would look something like this. And if you were to look across these multiple scans like this, it would look like a stacked chromatogram, basically. And you could look at it from that perspective. And so the idea here was that instead of trying to analyze any one of these scans individually, you could just look across this way and see all the fragment ions that you would extract out of these spectra instead of all of the fragment ions that existed in these spectra. And that simplified the interpretation quite a bit. Okay, so Rudy kind of mentioned some of this stuff, but there are a lot of caveats to this method. It's not as spectacular in some ways as you might imagine. So this is a pretty wide range, and you're typically going to see a peptide, but it's not necessarily going to be centered in that range, right? Rudy was talking about collision energy optimization for particular peptides, and you can optimize the energy for this middle of the window, but you don't know what peptides are going to be there, so you can't optimize it based on a peptide by peptide basis. So this is a major issue, right? You guys remember what that was? What charge states are the peptides we're looking at? They're not all charge 2, right? Charge 2 to charge 5, charge 6, something like that. So you have to pick one collision energy for the entire range, right? So typically we would pick 2 or 3 because the vast majority of your peptides are charge 2. Maybe charge 3 is a reasonable enough compromise. But this charge state energy is definitely not optimized for that particular peptide, even from a DDA perspective, let alone from an SRM or PRM perspective. Okay. As we said before, there are lots of co-eluting other fragment ions that are coming from other peptides in that same precursor isolation window. So usually there are multiple peptides. I've illustrated 3 here. Usually there'll be like 20 instead. So these spectra still are pretty messy. Another important thing is that there are edge effects to this. So a quadrupole is a mechanical device. It's not perfect. It's designed to transmit really well across a range, but it's not going to transmit perfectly every ion in that range. So if you say I'm interested in going after the 784 to 808 range, it's going to transmit mostly the stuff in the center pretty well. The stuff on the edges of that window are just not going to fly quite as well through the quadrupole. And this depends quadrupole to quadrupole. So the segmented quads by Thermo in their more recent instruments tend to be pretty good, but the older quads that they were using for the QEs ended up being kind of like really just designed well for DDA. So they would provide a lot of really good signal in the center because they were heavily optimized using DDA as the standard, and where you actually centered your windows around something. And so you ended up actually getting pretty significant edge effects as a result of this. And so Rudy's group is actually, because they're focused mostly on tops, have found that because they can't have access to these segmented quads, they end up actually having to play lots of tricks to be able to get good transmission of all peptides across this range. We'll talk about some of that tomorrow. Okay. So, so what does this data sort of look like? This is a particular peptide that I pulled from one of my experiments. This is superoxide dismutase. It's a +2 peptide from a human peptide. This is from HeLa. So if I extract all fragment ions for this particular peptide from superoxide dismutase, this is what I end up seeing. So each one of these different colors is a different fragment ion. And so here the blue fragment ion is most intense, here the black one is, here the green one is, here the light blue one is. So it becomes really kind of tricky to say, where's the peptide? Which one of these peaks is the peptide? In the end, it's actually this one over here. That's really small. And if you were to zoom in on that range, the way that you can tell that it's that peptide is because you see a lot of these fragment ions coming together at the same time, right? So you say, all of these fragment ions collude with each other, and that becomes my metric for being able to say, is this a peptide or not? So hopefully in the other places, that's maybe not as clear. So this is one peptide from superoxide dismutase. Here's another peptide. This is a +3 peptide from superoxide dismutase. Again, shows kind of this kind of messy chromatogram if you extract across the entire range. And unlike PRM or SRM data, we have the entire range that we have to extract across because we haven't been able to retention time select or window in retention time for a particular peptide. So I'm going to tell you this is where the peptide is, but what is it? Is it this? Is it this? I want to show hands. How many of you guys think it's this? How many of you think it's this one? It's like 50-50, right? So Brendan said this one, Olga said this one. It's this one. And the question is, how did I know that? Like that's pretty hard to make that call from this level of data. But I promise you it is. The way we know is because we have we have prior evidence. Because people have been analyzing HeLa for generations at this point. Maybe not with mass specs, but now we have a huge wealth of data about HeLa, even in most people's labs, actually. And so we know sort of how peptides behave in the mass spectrometer. And so we can use information for how we've seen that peptide before, say for example from a library. We will typically end up seeing a fragmentation pattern that looks sort of like this. And for this particular peptide. And then what we extract out of the sample is this. And we can say, well, these are pretty close. You know, Y8 and Y9 are pretty high. Y2 is high, but Y2 isn't very selective. What's the likelihood that Y2 is the same? Let's start out here. What's the likelihood that any spectrum has Y1 in it? Has a Y1 for 147. That's lysine. It's like probably half of them, right? Half of them have Y1. Half of peptides have Y1. So virtually, given that we typically see like around 20 peptides per sample at any given scan time, every scan is going to have lysine Y1. Every scan is going to have arginine Y1. So Y2 actually is selective only 20 times that, right? So you get arginine lysine, and then another 20 times that is 40. So 1 out of 40 peptides will have Y2. So Y2 really isn't necessarily a very good signature for this, even if we see a high measurement for it. Does that kind of make sense? You guys get that? Yeah. So if I look at this, I can say, you know, Y10, Y11, Y12, I see a nice ladder there. I see the same ladder over here in my library. That's pretty much kind of the nuts and bolts of how the algorithm sort of figures out, or how Skyline figures out that this is the right peptide. One thing that's, you know, let's think about this a little bit and about what this sort of data looks like. Here I see in the library spectrum, I see Y8 and Y9. Y8 is higher than Y9, right? But in my sample, Y8 is lower than Y9. Why is that?
Collision energy.
It's definitely possibly the collision energy. Is there another possible reason that it could be? Well, if it's proline, then it should be just as high in the library as it is for the, unless it's collision energy misoptimized, which definitely could be.
They are pretty close. It could be just stochastic as well.
Could definitely be stochastic.
The fragment of another peptide contributed to the Y9.
Yeah. So in this particular case, it's actually that one, where what we see actually at the apex of this spectrum is that Y8 actually is higher than Y9 rather than in the sample. This indicates that there's actually a contamination of that measurement. And let me show you what that contamination looks like. So this signature here is the Y9 signature right there, that one that goes pretty wide like that. And that's clearly been interfered with by another peptide at roughly the same time point. But we see enough of these green ions, these ions that we feel confident in that they're eluting together to be able to say that this peptide is actually present here. And so that's actually what we can do here, is that if we had a computer program that could go back and say, well, this fragmentation looks the same, and these fragment ions seem to co-elute with each other, we would trust the detection at this time point more than the detection at that time point. Does that sort of make sense? Okay. So what's going on here, actually? This is a phosphopeptide. This particular phosphopeptide is phosphorylated at this serine 2481. It's the signature for, this is a phosphorylation on mTOR. It's the signature for mTOR being in the mTOR2 complex formation, typically. So what's that? It's got exactly the same precursor mass. It has many of the same fragment ions.
Different position of phosphorylation.
Yeah. So this particular peptide actually has 5 different serine, threonine, and tyrosine acceptors. And it's clearly phosphorylated at multiple places in this particular experiment. And so we end up having to make a call in situations like this, what's actually going on. Let me show you what this sort of means. For example, I've got this peptide here where I see phosphorylation at one site and phosphorylation at another site in this, 2 different serines. Well, actually, if I look at all the fragment ions that are associated with these, I actually see a nice trace there, indicating both forms are present. If you end up looking for fragment ions that are specific to a peptide, you can say that this is the form that is related to phosphorylation at one site, this is a phosphorylation at the other site. But you have to go at this level of looking for specific fragment ions. You can't just look for a signature. Now this is true not just for DIA data, but because these guys share exactly the same precursor, this happens for PRM data as well as for SRM data. Because you're isolating these peptides using the same fragment ions for the most part. Okay. So here's another question. What's going on here? Here I'm showing a skyline trace where I've got precursor scan up here and a fragment ion scan here. These peptides have exactly the same precursor, but many of the same fragment ions, exactly the same fragment ions, but many of the same precursor ions, but not all the same precursor ions. This monoisotopic precursor ion is absent. Does anyone know what this might be? It is deamidation. So in this particular situation, we actually see a really good signature for what we're interested in measuring. This was a peptide that a friend of mine was analyzing. She left these samples in the -20 for, I think, 8 months or something like that, came back and reanalyzed them. Even in the -20, they degraded. These degradation products are important to acknowledge, but it's also important to know that this can be a problem for picking peptides, right? So if you were looking for the precursor scan, you might say that this is the form, and if you were looking for just the fragment ion scans, you might say this is the form, but really they're both the same thing, or really they're both the same biological important signal, potentially. Okay. So I hope I've instilled in you the fear of looking at this DIA data at this point, because it is pretty complicated trying to interpret it. There have to be some reasons why we're looking at this data for us to deal with all of these caveats and to move away from DDA or from SRM. I want to show this in comparison first to SRM because Rudy showed a nice example of DIA being better than DDA in some circumstances already. So from the standpoint of SRM, which you guys, for the most part, or PRM, you've seen already, the way you try to do your sequencing workflow or your analysis workflow is before you even start, you have to come up with an idea that you want to look at. You want to look at like all peptides from the mTOR pathway or all peptides related to the proteasome complex, where you have to have some hypothesis that you are interested in ahead of time. You then have to pick certain peptides out of them that you think are good. Either you got to buy them or you got to say, well, this one seems reasonable, so let's go look for it. You have to figure out when you're going to schedule for that peptide. Either you got to do a whole bunch of preliminary runs, or you got to scan for, or you got to synthesize these peptides and look for what they look like, or when they elute on your chromatographic time space. You got to pick which transitions you want to go after, and then finally you can do data acquisition, probably to find out that your biology was wrong. And then you got to go back to the beginning and then pick some more peptides, or go back and do some more transition refinement to figure out, this transition worked really well in my test case, but it's interfered with. So this process is constantly requiring you to go back to the instrument and reacquire and reacquire and reacquire. And this is a lot of time and effort. And to build a quantitative assay, realistically with SRM, it takes months. We're talking about sitting down with the instrument for maybe 4 or 5 months to build an assay for a handful of peptides that is actually robust. So I think the biggest advantage of DIA is that it kind of flips this on its head. You can acquire data before you even come up with an idea for what you want to look for. So you acquire data, you pick some peptides that you are interested in looking at because you want to look at the mTOR pathway. You select for those, you extract them out of your raw file, you transition refinement on the fly, so you can say, well, this transition isn't very good, but this other transition is pretty good, so let's go with that one instead. And if you find out that you wanted to add some more peptides into the mix, you can just go back and look at that same raw file and just start looking at that analysis or data set again. So this is a huge benefit over, over looking at SRM or ERM data, at least in terms of the overall workflow. Most of it can be done at your desk and relatively quickly. You don't have to keep going back to the mass spectrometer or bugging your tech to process or build more sample or whatever. Okay? Rudy showed slides sort of like this, but I think this is pretty important. DDA is a good method for profiling data, but I think as, or peptides and proteins, but as we are improving methodologies with DIA, we typically are seeing at this point now somewhere between 20 to 50 to even 2 times as many peptides as we would typically see in a DDA search analysis method. And that's, I think, a really strong case for using DIA, but it's not the only case for using DIA. I think the biggest issue is there's a huge amount of stochasticity here with DDA. So these are 3 different replicates of the same sample injected one right after another, right? Just one right after another. And yet still, they only agree on peptides 60% of the time. And this is a pretty good example, right, in terms of this is the same sample injected over and over again. We're not having to deal with biological instability or technical replicates as a result of different digestion on different days or anything like that. This is just the same sample over and over again. This is actually much worse if you're starting to look at phosphoproteomics, where you might have the overlap between 3 different samples be around 40% or a third of the peptides actually are one on top of another. And that actually has to do for a wide variety of other reasons. I think the biggest advantage of DIA is that even if you're analyzing these data sets independently, which with Skyline you don't have to necessarily do, but even if you are analyzing them completely independently, they typically say the same thing. And so we get a much higher overlap, such that the overlap here is actually larger than the number of peptides we were identifying from all 3 of those samples individually. Okay. Rudy also showed a slide similar to this, but I think let's look at it in a slightly different way. This is some data that was collected by a colleague of mine, Lindsay Pino, in Mike's lab. And this is the coefficient of variation across all of the peptides that she acquired in her experiment using this 24 MC wide window DIA approach. And what we find actually in these types of experiments is that if you do sort of your typical analysis paring down that you would do with DDA, sort of like 1% peptide FDR, at least 2 peptides per protein. Here we only have this additional 3 transitions as a minimum for doing quant. We actually find that our quantitative levels are pretty good. The majority of peptides here are below 10% CVs, and that we see about 90% of the peptides have at least 20% CV or less on repeated injections. And so in the end, with these types of experiments, we end up being able to resolve a lot of the sort of technical reproducibility issues that you usually have with DDA. And now all of a sudden the bigger issues that you have are these sample prep or biological variability, which is more the land where you want to actually be in. Okay. And as I said, the median CVs for this data set in particular with yeast were around 8%. And we find that this is fairly typical. With human samples, it might be slightly higher just because there's so much more signal in those samples, but it's not that much worse, actually, to be honest. Okay. So just to give you kind of a rough idea of how we analyze this data, again, tomorrow we're going to do a much more in-depth, detailed look at how software analyzes DIA data. But typically, as I said, you would go through this pipeline that we discussed earlier. This section here of peptide selection ends up being usually the most important selection. How you choose what peptides you want to go after. And there are a lot of different philosophies for this. So one philosophy is you could take like a normal search engine strategy like with Comet and just analyze all tryptic peptides in a human proteome or a yeast proteome. And that's possible, but I want to show you some examples of why that's kind of hard to do. Yeah, okay, great, perfect. I'm just going to do like a really simple example in Skyline. So this is just a file that was collected by a colleague of mine, Jarrett Eggerson, also in Mike's lab, or was in Mike's lab. This is just 2 yeast proteins that he extracted out of a 1 DIA run. And I just want to show you what this data actually looks like in the hands of what you're going to be looking at tomorrow, basically. This is and you guys have all, did anyone skip out on the Skyline stuff earlier? Great, okay, so you guys have all seen this sort of thing.
Are you sure? Really? Everybody was here for the Skyline course? No.
Oh,
So,
okay.
Who was here for the session 1 Skyline course at the, not that? Who? Okay.
Nice, not bad. Okay, great. This will make our lives a little easier tomorrow. So this is a particular peptide that Jarrett was interested in looking at. If you look at this sort of naively, this is again a huge amount of signal to be able to interpret. One of the things that you'll notice early on is that if I go to transition split graph, what I'm showing here on the top, these are the precursor signals, and here are the fragment ion signals. And as you can see, the order of magnitude difference between these is actually pretty huge. There's maybe a 50-fold decrease in your fragment ion signals versus your precursor signals. So if you're looking at this sort of naively at the precursor, all you'll, or at the mixed level, all you'll see is precursor signals. So going through this is actually kind of tricky to be able to say, where is this peptide? Here is the peptide that's selected by Skyline. This is what Skyline thought was the right peptide, and you can see it by these bars here. And so here's a great example of DIA just like working wonders. This looks like a beautiful peak. It looks like a beautiful selection from Skyline. Right? Anyone could probably say, yes, this is definitely the right measurement. But if I go down and look at this particular, so this is just one peptide down, and then if I just right click and then auto zoom on the best peak, this is the peak that Skyline picked. This, I mean, man, this looks terrible, right? But this is still, Skyline has given, all of the chromatograms for that particular peptide and said, figure out which one's the best one. And there's so much signal across that amount of time point that it's just going to pick something somewhere, right? It's going to make a call. And this is what, again, all of the DIA methods are going to make a call at some point, and they have so much data to work with that it's pretty complicated to try to figure out what's real. You've got to really heftily, manually validate this stuff. If you look at it sort of naively like this, just enter in a bunch of peptides and say, it's peptide. If I look down at this one looks great. This one looks kind of sketchy. This one looks great, really terrible. And like if you were trying to figure this out from, trying to naively look around this data set for where this peptide is, it would be really hard to say, where would this in my data set? Does it kind of make sense? Why this is actually a really analyzing it naively from a peptide basis is pretty difficult. Okay, so why is that, right? If you've got a particular, maybe 20 different tryptic peptides, and these are fully tryptic peptides for that particular protein. And the reason lies, there are several aspects to why that might be. And I think this is a pretty good example. So this is a particular peptide. This is Cas-C1. It's a transcription factor. And these are the 40 different peptides that are associated with it. And we ended up synthesizing this protein and then analyzing every one of those peptides using SRM and looked at the intensity of the fragment ions that came off of those. So this would be the transition response on this axis, and this would be the peptides ordered in intensity on the mass spectrometer. Because we synthesize these peptides, they're all equimolar, right? There's no processing here, it's just in vitro synthesized. So these should all be at exactly the same level because the last thing that we built onto these after a synthesis was a GFP tag, and that's what we use for enrichment. So we know we've got full-length reads here, or full-length protein here. So we end up seeing here, this is about 3.5 orders of magnitude in dynamic range. And the peptides that fly really well up here do so much better than the peptides down here. Being able to select which peptides you need to go after is pretty hard if you were trying to measure across this entire range. There's almost no way that you would ever, in a normal proteomic sample, be able to see these things down here, despite the fact that they have exactly the same abundance in the mass spectrometer as the things up here.
Could there also be digestion issues?
Yes, yeah. There are a wide variety of reasons why there's this level of dynamic range. One of them is digestion. These, for the most part, were pretty heavily digested, but there can be lots of different types of digestion issues, not just miscleavage. You can actually get additional digestion at sites that you wouldn't necessarily expect. As Rudy was showing earlier, there is at like the 2 orders of magnitude down level, you end up seeing a lot of different stuff that is caused by trypsin, or different weird cleavages that are caused by trypsin, just normally. But yeah, there's definitely a lot of reasons why this response could be fairly low. So if we look across, and this is a data set here of about 700 different proteins, this is the intensity, the order of magnitude difference between the highest responder and the lowest responder. So that one that I just showed you was about 3.5. That would be right around here, right around the center of this distribution. There's a staggering amount of difference in response for different peptides in a different protein. So here up at this top level, there's 6 orders of magnitude response between the highest responding peptide and the lowest responding peptide, despite the fact that they are at the same equimolar concentration. Okay, so choosing which peptides you're going to go after is really important for making this decision. And going after peptides that you're not likely to see really gives you a lot of trouble. And you end up with these situations where you extract out a peptide that we're really confident that that protein was present in that sample, but that peptide wasn't necessarily present or wasn't necessarily as strong a flyer as we would want it to be able to make a call using Skylab. Okay, so there are a lot of challenges in trying to analyze this data. The big one is presence or absence of a peak of a peptide. Choosing which peak is the right peak. Is it down here in the chromatogram? Is it up here in the chromatogram? Setting what your integration boundaries are is a pretty hard process, and that's one that we'll talk about tomorrow a bit. And if you're just doing this sort of naively, it's really hard to assign a p-value or confidence to this measure, and you really need to, because a lot of those peptides actually aren't present at the levels that you would need to be able to see them at, right? Or they're not, they don't provide enough signal at the level so you would need to see them at. So realistically, it's pretty hard to be able to do this type of work where you're trying to analyze ultra-big peptides. I'll talk a little bit tomorrow about a method that actually can do that, but it is a pretty difficult problem to try to think about. Another sort of strategy that you might have would be just, well, could we predict all of the high responding peptides And we tried that as well. I would recommend not going down this road. It's maybe not as fruitful as just looking at a lot of previous data that's already been collected. As I said, we've, as a field, analyzed most of the samples that we're interested in to death. We already talked about plasma being analyzed. You know, what was it? A $250 billion worth of money went into analyzing plasma. There's tons of data on the internet about analyzing plasma. There's tons of data on the internet about analyzing HeLa or many human cell lines. And you can also collect it yourself as you want. So there are these sort of 3 different strategies that I think we'll discuss in more detail. One of them is thinking about DDA spectral libraries that we'll talk about today. And tomorrow we'll talk a little bit about DIA chromatogram libraries, which is an approach to develop a DIA workflow, an entirely DIA-based workflow. And tomorrow morning, if I remember correctly, in the SkyJam session, there's a session about how to analyze peptides identified by DDA directly. So if you take your sample, inject it using DDA, and then take your sample, inject it using DIA one right after another, you can relatively easily transfer over your detections in DDA to your detections in DIA. And say that because it's the same retention time, same fragmentation pattern, they know exactly where it should live, you can move that interpretation over immediately. This requires twice as much sample, right? So that's bad. And you're also limited to only the things you can detect with DDA. But it is a way to actually get a DIA workflow off the ground with relative ease. So Brendan's going to talk a little bit about a data set, or go through a data set tomorrow doing that.
If you okay, take not presented in your the chance of
Yeah, yes. So then you need to look at some of these all-trophic peptide strategies, or buy the peptide and synthesize it yourself, and see what it looks like on your instrumentation that way. Or construct your own library, or some other sort of strategy around those lines. But yes, as I said, if you're going after or trying to analyze DIA data for peptides blindly without any kind of additional information, it can oftentimes be pretty hard to make the call as to what is a true signal and what is a false signal. Does that seem reasonable? Okay. Okay, cool. So, spectral libraries, I think, are the strategy that the Aebersold Lab has really dug its heels into, and I think it's a very effective, very good strategy. One of the nice things is it's kind of a feel-good story. We can reuse a lot of our old data that has sort of been wasted and gone otherwise unnoticed after publication, and it makes us, it makes me feel good to actually use some of that old data. But there are lots of reasons otherwise to want to use that type of data. There are, I think, 3 big reasons that people would typically think of for using a spectrum library to do searching. And we talked about this a little bit earlier, but probably the most common one that you would think of is that you know what fragmentation that peptide is, roughly. And you know roughly what retention times that peptide has, and you have a much more narrow pool of peptides to have to go out and look for. What I'll argue actually is that while this is probably the order in which you would come up with for how important a peptide library actually is, I would argue that maybe the bottom up is actually the more useful narrowing down of your analysis or interpretation. So fragmentation is, I think, a big, it's very helpful to know roughly what the fragmentation patterns are. This is a selection from a paper from Kuster's lab in proteomics, where they were analyzing a whole bunch of peptides, I think about 60 or 100 peptides, over and over again, a whole bunch of different charge states and collision energy optimization parameters. And one of the things that they noticed was that that collision energy matters a lot, like what collision energy you set matters a lot, and that collision energy means something very different from instrument to instrument. So for example, here is a fragmentation pattern from a LUMOS scan for this particular peptide, this FLF peptide, and here is the same collision energy for QE, and done as a butterfly plot. The red bars here indicate the sort of map, the error in intensity. And if you look at, it's very easy to eyeball this and say those are completely different spectra, right? This top one and the bottom spectrum is. You can sort of calibrate these instruments against each other. So this is a LUMOS collected again at 32, and then a QE with the collision energy set to 26. So a pretty different collision energy setting actually gives you a much more reproducible spectrum with what you were typically getting with the LUMOS. But this actually varies on a peptide by peptide basis. It's never perfect. And so I think this is an important caveat. Number one is you kind of have to know the source of your spectrum library and how it was acquired. It's really good if it's acquired on the same instrumentation that you've got, but it needs to also be roughly the same collision energy that you've got as well, right? Another aspect to that is that the difference between a DDA spectrum library that's collected using normal DDA settings, you know, like with collision energy optimization for +3s and +4s and +5 peptides, is that those actually have a pretty significant adjustment in the collision energy. So for example, if you're assuming a +2 fragmentation pattern from your DIA acquisition, a +3 is actually going to give you effectively a shift of a +2 in normalized collision energy. A +4 will fragment the way as if it were run with +4 NCE. So they actually have a pretty big shift in terms of the fragmentation pattern. This is here a shift of 6. Obviously, this difference is pretty significant, but this shift of 4 is nothing to sneeze at. Is sort of what I'm trying to get at. Does that make sense? There are different camps that are trying to build DDA spectrum libraries that are all acquired with the same collision energy without any collision energy ramping for specific charge states. The Ebersol lab was trying to pioneer this. I actually don't know what happened to that library, if that exists in the wild or not. But they were basically trying to acquire even the +2s and +3s, +2s, +3s, +4s, all as if they were +2 in terms of the collision energy. That's definitely one way to go. At least, even though it's not optimized for that spectrum, at least it will match what you expect to see, so that's a definite advantage. But that can be a pretty significant issue with analyzing these libraries. Yeah.
Could you mention again what's mapped in red on those butterfly?
Yeah. So this is sort of the mass or the intensity error, right? So this black and this black are the same. The red is the deviation between them.
But the tendency relative to each other, it seems actually preserved with these three peaks. Like, isn't it what's...
Well, this is the highest, and this is the highest here, right?
Yeah, but within a spectrum, doesn't Skyline rank transitions compared to one another?
Yeah.
Why should we care so much about absolute intensities in this spectrum as long as relatively they stay the same?
Yeah. And I would offer that 2 ways. Yes, it will select transitions based off of that, and so you will end up with the top 6, and maybe those transitions are there. But then trying to use that spectrum as information for where you call that peptide will be completely wrong, right? You'll call the different fragment ions as being more intense, and you'll actively look for them as different intensity, at a different intensity level. And so your scoring patterns, which are mostly going to go after those delta intensities, are just not going to be as precise. Does that make sense? Yeah. Okay. So retention times are definitely also another important factor that we can get out of these libraries. Usually retention times in typical GBA libraries are accurate to maybe around 5 minutes on a 100-minute gradient, 5%, something in that range. And that cuts out a lot of the search space. So if I only extract out a ±5-minute range, then I'll be pretty likely to get these peptides, and I won't have to look at all of the other sort of garbage around in space around them. That said, it's never quite that perfect. Typically, I think, Brendan, when we do DIA extractions, usually we think about plus or minus 10-minute windows. Is that about right?
Well, 7 and 5.
So, yeah, plus or minus 5. Okay.
But if the library is built on different, let's say that, it's a sequence, the retention time.
Then it's much more accurate, yeah. It should be much more accurate. That said, most people do some sort of a chemical fractionation to build libraries, right? And that chemical fractionation affects the matrix, right? So it actually changes when peptides elute as a result. And so even if you're running it on exactly the same instrumentation platform and the same column, because it has a different matrix background of peptides, it will actually shift around by a surprising amount, plus or minus 2 minutes. It's not as significant as this sort of thing is, but it is still much more variability than you would expect by default, right?
But if I have used like spectral library with a completely different gradient, like different effective length, then I better have a look at all the data I have there, right?
Yeah, so in just a couple slides, I'll talk about that.
I have a question. So if you have peptides with PTM and time drift is between the modify and unmodify is more than 5 minutes, you can still like match with the modify and unmodify the same. In order to calculate the percentage of PTM with modifications, so you think about this plus minus 5 minutes. The sum of PTM can drift 6 minutes.
Right, but that's actually in a different precursor isolation range typically. So like a phospho
So you
would
can
be, yeah, and you would think of it in a different way. Now that is certainly an issue for other sorts of peptides. Oxidized peptides will fit into that same, potentially in the same precursor isolation window. And I don't know if Mike is going to show the slides, but oxidation.
Yeah.
Yeah, I know.
So tomorrow you get to see some stuff around that. Okay. So retention times are definitely a feature. Mostly they do give you like maybe a 10% of the range that you only need to extract out. That said, I would argue that retention time and precursor mass actually scale quite close together. And so while this does give you some separation or some discrimination, it's not actually as much as you would expect. It's much more of a nice thing in terms of being able to cut out or call out a lot of the noise rather than improve the amount of signal that you're seeing. Okay. The third, and I think probably the most important factor, is that a spectrum library narrows down the list of peptides that you're interested in looking at. So if you're interested in looking at a HeLa spectrum library, say like around 100,000 peptides or 150,000 peptides, that's a fairly large library as human libraries go. But if you compare that to all of the peptides, and this is for just straight pure tryptic peptides, that's around 1 million peptides in a human basket. So we're talking about an order of magnitude increase in the number of peptides that we're looking at. For adding a single met ox, only a single met ox, not multiple oxidations, that is a fairly significant increase, like a 20% increase in the number of targets you have to look at. And if you were trying to think about human phosphopeptides, it's really like that is a much more staggering search space. And people have seen this sort of issue with DDase analysis, but here it's a much more significant issue relative to looking for those individual libraries. So a library of phosphopeptides is very valuable, I think, for those sort of experiments, rather than trying to go blind and just look for fragmentides associated with random potential phosphopeptides. Okay? Yeah.
What about the false discovery rate? Like, we also know from DDA that if we look and search against the two small database. It is also a problem. So when is the spectral library that small that it becomes an issue with the, what would you say?
That's a good question. There are different ways you can think about that. The original mProfit paper, which tried to come up with a false discovery estimate using a bunch of assumptions, was built around the idea that you were looking at SRM data and usually only 100, 150, 200 peptides at a time, and trying to make a call amongst just that many peptides. That approach, I think, works, but it requires a significant number of assumptions. We'll talk about that approach tomorrow. If you want to use a different type of validation approach, so like percolator, for example, I think Mike might be a better guess, but I would say percolator probably doesn't perform very well below 1,000 peptides, something like that.
Yeah, I mean, so you need to be able to train the support vector machine. So there is ways in which you get to resort to a fixed discriminant score, but currently that's not used. So you probably do need a minimum number of things to have.
Yeah. So
the other thing to remember is you're flipping the problem around too. It's like, so the reason you get into problems with such a small restricted thing is the question is, I have a spectrum. What might it match? So if I give it a very narrow list of things, all of a sudden, well, okay, it matches pretty well to this thing, but it's not really that thing. And in this case, what we're doing is we're saying, okay, here's a peptide. What evidence do I have of this peptide being in my sample?
yeah, so I have that slide actually a little bit. Just to sort of think about this, really what we're trying to do is extract out all of the fragmentides that are associated with a particular peptide across the entire retention time range or across a truncated retention time range, maybe 10 minutes or 20 minutes, and score it in time and assign some kind of score, whether it be a spectrum correlation between your required matches and your library matches, or mass accuracy score, some kind of a combination of scores, and extract out, say, hopefully there is a peak that is the most or the highest abundant peak in score space, and use that as your anchor to be able to say, is this peptide present or not at that specific time point. From that standpoint, you can use normal sort of percolator and other kinds of training algorithms to be able to decide what peptides are present in your sample. But the question is a little sort of backwards, isn't it? Instead of asking in a spectrum-centric way, where you've got 30 or 50,000 MSMS spectra, and then seeing, what's the best peptide that matches to this spectrum out of my entire protein sequence database, and getting a list of PSMs where you've got one peptide spectrum match per MSMS that you've acquired. So this is one measurement for 30 to 50,000 scans. We've kind of inverted this on its head, as Brendan says, where now we've got a list of about 1 million peptides or something like that, or 100,000 peptides in a library. And we're asking, if we extract that out, what is the best retention time for this peptide? Or where is there the most evidence that this peptide is actually present? And making a call for that specific point. And so instead of doing that, we're actually coming up with one peak or one point of detection per peptide, rather than one point of detection per spectrum. And this is sort of an interesting question in that we actually end up having to think about this as a problem for false discovery analysis, right? Where here we might have to false discovery correct against 50,000 PSMs. Here we actually have to false discovery correct against every single peptide that you searched for. So if the library is 100,000 peptides, then you have to false discovery correct against 100,000 peptides. If you're looking for all peptides in a proteome, it's going to be 1 million peptides instead.
I'm kind of a bit confused. shouldn't we be comparing our libraries against the databases? Because our libraries are not what we like. It's kind of the other way around. I would argue that spectral libraries in DIA, and this was my actual point, they are smaller than FASTA files from Unicode, and that's what you said.
Yeah. So here that might be 150,000 peptides in a human HeLa FASTA proteome, or sorry, a human spectrum library. It's still going to be significantly more than the number of spectrum.
The important thing is libraries are kind of a misnomer. These are not like this magical spectrum libraries. It's just some statistical priors, right? So you've got some retention time constraints, and you've got some, these fragmentines are a little bit better to use than all the fragmentines. As opposed to, but you can do it without those priors, without any retention time information, and without any knowledge of what fragmentines.
I have a logistic equation, but how retention time information from someone's spectral library would be used for my system?
I think Brian will get to that.
Can I one more thing about this that I'm just realizing as we're showing it is that, especially in the context of the question of should you search a bigger space, and isn't that problematic for the spectrum-centric DIA searching? An important thing to remember about the spectrum-centric searching is that when we assign the spectrum to one thing, and that excludes it from everything else. So if we don't have the thing that matches it in the database, then we might actually assign that spectrum to the wrong thing. Whereas there's no equivalent in this peptide-centric searching. We go in and we look at all the data and we go, did we see it? And there's no exclusion, right?
Yeah, so I think what Brendan is trying to get at is if you get an error up here, like an incorrect PSM, you actually still get a score for that PSM, a top score for that PSM. It's to the wrong peptide, but it's a top score. Here we actually, in a peptide-centric way, you actually get a wrong peak or a wrong time point is what's extracted out. And that's in some ways a little bit easier to sort of ignore or separate out, because typically, first it's going to provide less signal than the true time point would be, because you're just not going to have very many fragmentines that match to it. So from a quantitative perspective, it might not actually affect the statistics nearly as much. Like a false error at that level won't affect the issue as much. Does that make sense?
Not sure. If I will ignore the right peak, I will never get to compare those two.
If you know.
How is the wrong peak not as bad as the wrong peptide spectrum match?
Oh, so for example, if you've got two samples and you integrate it over here, and over here it wasn't in the sample, so you picked the wrong time point, that signal is going to be a lot lower than if it were actually in that sample.
Not necessarily. If I wrongly picked the more abundant species.
So yes, but it will probably only have a handful of fragmentines associated with it, not lots of fragmentines, not associated with that peptide. We can look at some of that data actually afterwards. I think moving on just to build libraries so that Brendan gets a chance to talk a little bit later. This I think is a good paper to go with. What's that?
I'm having fun here.
Oh, okay, sorry. Do you have a comment?
No, I have a question.
Oh, yes, sorry.
You showed this paper. When we try to run that protocol, SpectraST crashes on us. It has trouble with the iProfit output from two search engines. Is that something that we can try to figure out here? Why?
Oh man, I don't want to.
Well, you showed the paper. So.
Yeah, it's not my paper though.
It's your slide.
No, I would argue.
No, it's a very practical question.
We can give you the email address of the SpectraST. We can give you the email address of the SpectraST developer.
Yeah, that
Okay. Yeah.
Yeah.
That we can definitely do. I think that it's probably not going to be as big of a deal as you would think.
No, it's
using
definitely,
multiple search engines.
something small, but
Yeah.
obviously too small for us to find it out. Yeah.
We're also going to talk a little bit about strategies tomorrow where you don't have to build libraries like this. So maybe that might pique your interest more. Hopefully.
Or Or you can use Skyline to build libraries.
Yes, and so actually, I think the method that we kind of promote here now is this idea of doing that offline fractionation, generating a DDA list, searching those peptides, and then building the library just straight in Skyline. I don't know if you can use multiple search engines.
It doesn't have to be.
Okay, perfect.
Yeah.
Yeah.
Yeah, but it's not a necessity.
The Skyline Builder is a much more robust tool, I would argue, for doing this. So that might make your life a little bit easier too. Okay. We were talking about retention times. This is, I think, a really important point that if I use someone else's library, how is that going to be helpful to me using very different column chromatography, using a different packed column, potentially using a different resin or anything like that? And I think one way to get around that is to use what are called IRT peptides. And I think this is a bit of a misnomer because any peptide can be an IRT peptide. It's just a retention time standard that you can scale to a dimensionless retention time point. It doesn't matter what it actually is or what it represents. It's just a way to get all of your samples in the same time point. So for example, IRT peptides I think are really expensive. We typically use the Pierce peptides, which are retention time standard, which are a bit cheaper. But you can use any peptides that you wanted. If you synthesize some peptides that are useful for your experiment, you can use those as well. It doesn't matter what they actually are. They're just some measurement, some yardstick, basically. Okay, so the idea is that each of these peptides has a value in this sort of this dimensionless IRT space. And when you measure these peptides in your sample, they'll give you a specific retention time. And you can map those onto an IRT list. So for the peptides that you are, so for example, this peptide elutes quite quickly and has a negative IRT for whatever reason. This peptide here elutes at around 50 minutes in my experiment and has an IRT of around 60. It doesn't matter what 60 is, it just matters that it's consistent, okay? But the big advantage here is that you can take a different analyte, say analyte A, a different peptide, and map it onto the same list. And then you can say, okay, A elutes at around 23 minutes in my experiment, but because I've got this nice line of IRTs, I can say, well, right here is where it should be. I'm going to now assign it an IRT number of, I guess, around 3, right? This one, B, I saw it around 50 minutes in. I'm going to assign that an IRT around 60. Does that make sense? So it's a way to kind of like assign other new peptides IRT values. And so actually, if you wanted to build your own IRT standard, you would only need to buy like the Pierce standard or the Biognosis IRT standard once, and then map it to your peptides in your experiments, and then just be done with it. The important thing is going backwards. So then you can map it to this is where the IRT would be, and then and stick those into a spectrum library. Now, when you're analyzing a new sample, and so this would be as if you were taking someone's IRT experiment from a different library and trying to analyze it in your experiment. Well, you've got the same IRT peptides now in your experiment. And again, it doesn't matter what they are, just that they are consistent amongst the library, within your sample and the library. And you can take those IRT measurements from before, for A and B, and you can map them onto a totally different retention time. So here, this time point is actually half as long as the previous one, yet we can still come up with measurements. So now, A, which we said was 3 here, is now 1312 right now. B, which is 60 IRT, which we said before was 50 in retention time space, is now mapped to 25 in retention time space. Does that make sense? So this is a way to develop a retention time standard as you go, using all of your peptides in your experiment. And use that to predict retention times for a totally different gradient or a totally different data set. And this can actually be scaled at large, and we've done this a bit, which is to actually take a bunch of these IRTs that we're pretty confident in and map them to our handful of peptides, and then use what we think of as an alignment run. So we'll take one high complexity sample, so something with thousands of peptides in it. So for this experiment, we were doing phosphopeptides. We injected a pure standard into our phosphopeptides, and we're able to generate IRTs for our phosphopeptides. For every one of the phosphopeptides we were able to detect in this run here. So now all of those phosphopeptides we now have IRTs for, and we can sort of extend that to another sample now. So these now have IRTs. We can look at other in-house runs and be able to say, well, I didn't put my IRT peptides in those runs, but I did have a bunch of these other peptides that I found in this anchoring run over here too. So now I can take all of those and actually map those to IRT peptides effectively into the IRT dimensionless space, and now give myself retention times that I can normalize for every one of my in-house runs from previous data sets, even if I didn't have those standards in them. I can even do that with external data too. So it doesn't even have to be run in the same lab. It's just you need the same peptides in those samples. Does that sort of make sense?
How much of a retention time shift is acceptable for you when you look at your data?
It depends on what I'm going after. I typically expect there to be, if I'm looking at DDA data, I typically expect there to be around a 5-minute retention time shift, especially if I'm using different chromatographic conditions and different potential matrices. So for example, if I build a background on HeLa and I'm analyzing MCF7, it's a different matrix, so I might make different calls.
Or for fractionated.
Or fractionated samples, yeah. Yeah. Okay, so one last slide before we quit, or I quit, and then Brendan speaks. Is that there's a lot of publicly available libraries where you can go and download a library to suit your specific needs. I typically prefer to use this SWATH Atlas library. This is where the Pan-Human Libraries lives from Aebersold's lab. It's where a bunch of other libraries live. It's not perfect, but it is pretty good for the libraries that they have. They don't, for example, have a mouse library, but they do have like a tuberculosis library, because it's just whoever random wants to submit a library can do it. But it is all processed through a centralized pipeline, and it's pretty standardized. So that's, I think, a fairly safe library set to use. This NIST library, the ChemData library, is another good source for libraries. One caveat of these libraries is they don't actually include retention times. That's too bad. This library here, Phosphopedia, is the library that we've actually built for phosphopeptides and contains tons of human phosphopeptides as a thing to be able to map all of those to. It does have retention time standards. There are a lot of different sources for libraries. Just be careful about who generated the libraries and what sort of conditions they used, and whether they make sense for your experiment as well. So for example, you mentioned earlier about CID versus HCD. Like most of the libraries in this NIST data set are actually CID data sets. So if you're using HCD, that might be an issue, or beam type instrument, that might be an issue. There are some libraries in the SWATH Atlas. Like there is one mouse library, but it was collected on ion trap data, so it's not really helpful for most people. So knowing where your library came from, I think, is really important for being able to make use of it.
So you really think that if I have a library on QExactly, and then I'm switching to orbit trap, I'm doing a mix of them, and I'm converting the DIA on orbit trap is not good?
I think mixing between HCD and CID is not good. You actually are almost as good. I've done this analysis. Your base.
No, but both of them in AC. Both the orbit and the QExactly in AC.
That's fine.
That's fine.
That's fine. So same fragmentation pattern, fine. You can take a QTOF library. Pan-Human library is a QTOF library. You can apply that to a QE or to a Lumos, not a problem, as long as it's beam type fragmentation. If you're using CID fragmentation, you're basically just as good off if you just threw away all the fragmentation data already. Like you get very little out of it, to be honest.
But the CID and ACD fragmentation pattern are very similar.
I would argue that they're not similar. They're similar enough for being able to pick a handful of transitions and hope that some of them work, but they are not good enough for doing scoring. So, for example,
The intensity of the ions is also fragment ions.
yeah, the intensity of the fragment ions shifts dramatically. So, using it as from a correlation coefficient perspective, it's not very effective. It is sometimes helpful for being able to pick the most abundant ions, but just as we were talking earlier, that doesn't help you necessarily for scoring where that peptide is.
I think you definitely wouldn't be able to use it for phosphopeptides.
Yeah, not such a regular.
Okay, cool. So that's pretty much all I had to talk about. DIA is a bunch of compromises. There are lots of problems with it. There are lots of different ways to do it. But I think overall it is worth your time and effort to try to explore this because it is a very powerful tool, I think, in our hands. I think for the most part, Mike and I have switched over almost entirely to doing DIA for our actual